In the previous two lectures, we had started focusing on PV diagrams, and we had specifically focused on the isothermal process, which was when the temperature stayed the same. In this lecture, we're going to try to tackle all of these other three, the adiabatic, isobaric, and the isochoric or isovolumetric. So we'll start with the adiabatic. Adiabatic is from the Greek word for impassible. And where that comes into play is that in the adiabatic process, we set the heat transferred equal to 0. And what we're indicating there is that basically heat can either not get in or get out because it's super well insulated. So that's one instance where it could theoretically occur. In practice, it's actually impossible to get something so insulated that there's no heat transfer. But we can pretend. We can get close enough that we might as well treat it as if no heat is leaving or coming in. And it also occurs, we can treat a process as adiabatic if it happens so quickly. So if the gas expands so quickly through an explosion, for instance, or is compressed so quickly that there's really not much time for heat to flow. Not saying that it will be exactly 0, but that it could be pretty close. And close enough that it's just easiest for us to treat it as perfectly adiabatic. And what I'm going to do is I'm going to show you then kind of what this looks like on your PV diagram. But before I do that, let's just go through the important part of this really is the implication. So if there is no heat, that means that the internal energy changes that occur are due entirely to the work being done by the gas or being done to the gas. Okay, so here I've kind of set up a preliminary adiabatic graph. And in the adiabatic, it's characterized by Q being equal to 0. And then if we go back to our change in internal energy equation, which is really just conservation of energy, it says that if we're not doing anything to add energy or take energy away from the system, then any change in the internal energy of the gas will be due entirely to what the gas does or what's done to it. So if the gas expands and expends 50 joules through expansion, then the internal energy of that gas will drop by 50 joules. And that's what this statement is saying. This is not a fundamental statement. It's not conservation of energy, which is what this one is. But it is very useful in the case where you have an adiabatic process taking place. And here I have my PV diagram, and I always kind of sketch in some isotherms. So this is my colder isotherm. This is a hotter isotherm. I get hotter as I go this way, higher temperature I should say, and we get colder temperatures as we go down towards 0, 0. The adiabatic processes are a little bit strange, actually. They're not isotherms. The temperature does change. So let's say that I have a gas, and let's do it this way. So I have a gas, and it starts off at this high pressure and a fairly low volume. And what's going to happen is it's going to expand kind of explosively. And through this explosive expansion, since we're not adding any heat to it, the temperature ends up dropping substantially. So you basically have this high temperature, highly compressed, very pressurized material, and we let it just expand. It blows up. And through the process of blowing up, the volume goes up, but the pressure goes down a lot more. And I discussed that in, I think it was lecture 5, I could be mistaken, what's going on with the pressure and the volume to make that transition to a lower temperature. In an isothermal case, what would happen is we would be feeding it heat the entire time that it would be expanding. And that would keep it at a constant temperature. But in this case, we're not allowing heat to travel in or to travel out. So what ends up happening is it rapidly expands to a higher volume, lower pressure, and lower temperature. And we can look at the other case where we have it starting off at this pretty large volume but a very low pressure, and it's cold. And we rapidly compress it. So we have this sort of explosive compression, so to speak. And in compressing it so quickly, we don't allow heat to escape. And so all of the energy that we're putting into the system goes into moving the particles faster, giving them more kinetic energy, more temperature. And so we've rocketed it up to a much higher pressure, even though the volume change hasn't been that great. And so now it's at a higher temperature than where it started. That's the basic principle behind adiabatic processes. Wherever you have explosive types of processes, adiabatic is typically involved in some manner. And one thing that we're going to talk about later on is where this comes into play with heat engines. So the first one here is isobaric. And if you recall from maybe chemistry or IEE, or even 7th grade science, this term, this part here, baric, kind of sounds like barometer, which is one way that we measure pressure. And iso meaning, once again, the same. So we're talking about a process that involves the same pressure. And that's exactly what I have here. So we have a constant pressure reaction. And so what this says is that if we increase the volume, what we're doing, an increase in volume occurs with an increase of heat and an increase in temperature. So we're keeping that pressure nice and constant. I'll show you what that looks like. Okay, so here you can see I have isobaric. We have a constant pressure. And what that means is that your work that's done is actually going to be easiest to calculate with isobaric than with any of the other processes that we've talked about so far, because we have a nice, consistent way of doing it. For instance, if I want to find out how much, let's say, whoops, that didn't work out. Let's say that we have this process and it's going from, let's call this point A to point B. So we're going from point A to point B. We're starting off at this low temperature, same pressure, but taking up much less volume. And then we're expanding it off to take up a much larger volume. And you might say, well, wait a second, if I have a certain amount of pressure, if I have this container, and initially we're only taking up this fairly small area, okay? And then we're changing it so that now we're taking up, and assume that these are the same width, a larger area. How is it possible that it's hotter? One of the things that we've talked about is that when you expand gases, they cool down. Well, the thing that you have to bear in mind is that you're expanding this against some sort of a force. So there's been, during the process of expansion, maybe there's some weights here that we're trying to lift up. Okay, so in any case, there's a force downwards. In our simplest case, a force of gravity from these weights. So that means that if we are expanding against this, then there must be some sort of an upward force that's at least as great, if not greater, than that force of gravity. And here, in order to get it to this point, we have to have at least as great of a force. So if you imagine that you have those particles inside of here, and they're bouncing around, it's not that big of a container, so maybe there's not that many particles. We're still left with the same number of particles down here. And they have to be able to exert the same amount of pressure. So you're basically the same number of collisions or the same vigorousness of collisions per second as in the previous case. They're going to have to be covering a lot more ground in order to collide with this often enough with enough energy to keep this from falling back down. So the only way that that's going to happen is if we add a lot of heat to this. So we had to add, and I do this here, oops, I guess we'll make it a nice hot pink color. When we do this, when we go from here to there, what we're really doing is we're adding heat. So we're adding heat in the process of going from this situation to this situation in order to make it so that it's possible for that pressure to stay constant. And you can see that just from the PV diagram, but it's also useful, I think, to have a clear understanding of why that's the case. Now, to get the work that's being done, in this case by the gas, you just take the area under the curve. And bear in mind that the gas is doing positive work. So an example of how this might look would be, let's say we want to find the change in internal energy. That's Q minus W. Okay, you might have something like 100 joules of heat added for 50 joules of work being done. And so you wound up with this change in internal energy of plus 50 joules. And you can look at kind of a different example. So here's a case where we're going from, let's call that C to D. So we're going from a high temperature, relatively high volume, to a low temperature, relatively low volume at the same pressure. And it's just the reverse of this. How do you get this to fall? Well, you have to reduce the speeds of these. You have to make them collide less often and less vigorously against the surface. So you have to take a lot of heat out of it, maybe put some ice cubes around it, that type of thing. And eventually it'll get back to this state, where it's more compressed, but the particles are much more sluggish. The final process here is almost certainly the easiest, although it might not be quite as easy to remember as some of the other ones. We usually call it isochoric, but another term for that is isovolumetric, which by now you should have caught on to the naming code. Iso meaning the same, volume meaning volume, volumetric, and it just says that the volume is constant. So what this tells us then is that we can increase the pressure by adding heat, or we can decrease the pressure by taking away heat, and we can change the temperature. But because the volume is constant, we can't do any work. And I'll show you that in the PV diagram. So here's our PV diagram. Isochoric says no change in volume equals 0. And what that says is that the work is 0. If we don't have any change in the shape of the container, or in the space that the container is taking up, our force wasn't effective at moving anything. So if I go back to my old standby container, whoops, once again, wrong tool. If I go to my old standby container, and we've got this filled, and there's some things here, some weights here and so on that we're going to try to lift. Well, if we're pushing up, but they're pushing down just as hard because of gravity, then the molecules inside aren't going to be able to expand this. Okay? Now this might occur because maybe this isn't slidable. So far we've dealt primarily with slidable tops. Maybe this is just the top of a container and it's very rigid. And so you've got these particles, and no matter how fast they might be moving, maybe they're moving really, really fast, they can't get this to budge. So it's very ineffectual. It's kind of like when I was pushing the table in class to show you that no distance means no work. We're not making it any more destructive. We're not raising anything up. We can be pushing as hard as we want, but nothing's changing. So no work is being done. And what that means is that our equation becomes much simpler for the internal energy. The change in internal energy of the system can only be due to heat then. So for instance, in this case, if I want these to go faster, if I want these to raise their temperature, the only thing I can do, the only option available to me, because I'm not changing the container shape, it's rigid, I need to add heat. And if I add heat to the system, the particles will go faster and we'll get a greater pressure. So for instance, if I look at this one here, let's say that I'm going from A to B. So we start off at this pretty low pressure, pretty low volume, not super low pressure, but you know, reasonably low, and we want to raise the pressure. Well, we're not doing any work. There's no area under this curve. There's no distance through which the force is pushing something. But we're just going to raise the temperature. And to do that, we need to add heat. And it's as simple as that. If I go from, let's call this C to D, here we're starting off at the same temperature there, but you know, we have this much greater volume, but a lower pressure. And that's indicative of the same temperature as this one. And we want to reduce the pressure. Well, how do you do that? You put some ice cubes around it. You do something to pull heat out of it, to take energy away from it, and it will cause the particles to push less hard against the sides of the container. Now, if the container wasn't rigid, the container would collapse when you do this. And you might have seen in chemistry, maybe they did something where they heated up some air in a container, and then they doused it in ice cold water. And the soda can might have collapsed then because of the lesser pressure. You also see this not from thermodynamics things, but if you take a bottle onto an airplane, you can have pressure changes occurring as a result of the altitude. And the net case is that if you cause this, in order to cause this change, or in order to cause a change in the pressure without changing the volume, you must be taking away energy or adding energy through heat. And just to reiterate the last thing here, When you have a direction this way for your PV curve, let's say it's like this, the gas is doing positive work, it's expanding, it's pushing against something. Here, this way, the gas is doing negative work, it's having work done to it, it's being compressed by something else. It's pushing against it, but the motion is still down that way.